introduction, what we said, we have the equation of motion. Is again this, I'm just going to say it's the full order equation. So this is to duplicate as much as we can the dynamics of the structure. And under complete we'll put many lines, because this is not complete by any means. Okay, the only complete equation of motion is partial differential equation, which describes exactly the dynamics. But once we discretize the system, then we lose some of the information, but I'll say it is as much as we can for complete description of the dynamics. And then now, once we have this, then our main job is to reduce the order to make it compatible with the dynamics of the control system. A practical controller. Okay, so the way we will do it, use the static condensation method. Or the Boolean reduction method. And all finite element packages have this model reduction in it.
Last time we showed that the Boolean reduction keeps the information regarding the potential energy of the system. Mm-hmm. We said nothing about the kinetic energy.
I'll do it. Yeah, we'll do it today. Yeah. And all this is done for the static condition. Okay, so now we will say the following. We'll say now, neglect the dynamics and only look at the statics. Then we have K delta is equal to F, and the reduction will be based on the following. I'll take the full order matrix of the stiffness of the system and then break it down into several block matrices corresponding to the degrees of freedom that we specify as secondary and as primary. And the S stands again for secondary degrees of freedom, and the P stands for primary. Okay, and I'll partition the stiffness matrix corresponding to these degrees of freedom. And accordingly, the full state variable of the system, I'll break it down to important degrees of freedom I will retain, less important degrees of freedom I will set aside, but then I will capture them after I'm done. So we can guarantee everything is working and the controller is working fine. So now, from the first set of equations, we can eliminate or determine or extract the secondary degrees of freedom in terms of the primary. So from here, I'll have KSS delta S, KSP delta P is equal to 0, or we have delta S is equal to minus KSS inverse KSP and delta P. And I'm going to call all this just a little transformation. Matrix R star delta P. Then now I can write the entire state deflection vector, and we call it delta O last time, and this will equal to delta S. I'm going to put it in terms of delta P as R asterisk delta P, and delta P in terms of delta P will be identity matrix, and this will equal to R delta P. Okay. Now I'm going to use this now in the second equation. In the second equation, we can expand, so we have KPS delta S, KPP delta P is equal to QP, and I'll replace delta S from here. So this will be KPS minus KSS inverse KSP plus KPP delta P, and this will be my QP. And then now I relate the primary degrees of freedom to the applied load on them, and the constant of proportionality is the reduced stiffness matrix of the system. And I'm going to call this P reduced delta P. Now I can calculate K reduced by this equation. But to do it, it requires that I have to get this inverse. So if we have large system and I have few actuators on it, so this is very small compared to this. So delta S is very large number of degrees of freedom I want to set aside. So KSS will be very large matrix, and it will be numerically inefficient to look at this inverse. So we can do this in two ways. As I was saying before, the model reduction is very large subject, and MATLAB also has another ways of doing the model reduction. So in the homework we'll show you, so you can compare the Gaussian with some of the MATLAB methods that are mainly electric engineering methods. Gaussian reduction comes from the mechanics of the system. Okay, anyway, so now we'll just say here methods for calculating the reduced stiffness matrix. So the first method, it says K R is equal to R transpose A and R. A and R. And the proof of this is I'm just going to look at R transpose K and R. We have R is this matrix. R asterisk identity matrix. And then the K is the partition matrix. KSS And then now the R transpose will be I, R asterisk, transpose. And then I'll expand this. So this will equal to R transpose KSS plus KPS times I. Okay? And then I'll expand from the other side, so I have R asterisk transpose KSP plus KPP. And then this is times R asterisk I. And then we expand this again. So this will equal to R asterisk transpose KSS and then R asterisk plus KPS R asterisk plus R asterisk transpose KSP plus KPP. I'll come to the first term and replace R asterisk by what we have here. So I'm going to take all this out. And the first term will be R transpose KSS. And then I'll replace R asterisk by minus KSS inverse K SP. And then here plus KPS R asterisk plus R asterisk transpose KSP KPP. Okay, now if we look at these two terms, they cancel because this is identity matrix, and then this is exactly like this, so this is 0. And then now the remaining two terms, the first term, I'm going to write it like KTS, and then replace R asterisk from what we have here. So this would be KSS inverse minus KSP, KPP. And if we look at this, and this are the same. These two are the same. So now this says that R transpose KR is equal to K reduced. Now in this formulation, it's all multiplication, matrix multiplication. There is no inverse, there is no like matrix inverse. So this is an easy way of calculating the reduced stiffness matrix. Now, the second way is the Gauss Elimination method. And again, I have the stiffness matrix. So I'm going to do row reduction on this set of equations. And I'm going to put it in a canonical form by using the Gauss Elimination method. So I'm going to make this term identity matrix. Okay? So to make this term identity matrix, I have to multiply the entire row by the inverse of this. So I'll have here KSS inverse, KSP, and then this stays as it is. And then when I multiply by the inverse, this is 0, stays 0 as it is. Now to complete the Gauss elimination, I'm going to multiply this row by KPS, or negative KPS, and add it to the second row. So I eliminate this term. So now this becomes 0 matrix. So I'll take this row and multiply it by KPS minus. And then add it to the second row. So this becomes KPS times I, and multiply it times this term. So this would be KSS inverse KSP, added to this row, KP. Now I'm going to multiply this row again by KPS and eliminate this term. When I multiply by this by KPS, take the negative. I multiply it here and add it to this. This does not change. This stays as it is. So now we're done. Now I'm going to take this and partition it. Let's see the result, what we have. This term, again, is exactly the same as the reduced stiffness matrix. This term is the negative of R star. So now, after we do the Gauss reduction, this is identity. This is 0. This is minus R asterisk. And this term is K reduced. So the second method for calculating the reduced stiffness matrix is to do Gauss elimination. This is the easiest way of doing this process. Why? Because the byproduct is also this R star. I can use it to reconstruct this vector. When I do my control and everything is done, I have delta P multiplied times R, calculate the entire vector. What we're going to show today, before the control, we'll show the eigenvalue problem. So you can see how model reduction affects the eigenvalues and how can we reconstruct the eigenvector of the system. Any questions?
We're still involving an inverse of KSS, which is normally a huge matrix, large matrix.
No. This is not done by, this is not inversion. This is done row by row reduction. So you take a pivot element, you divide by the pivot element. One row at a time. It's not block matrices. I'm gonna take this, we'll show you in the example. I'm not gonna invert matrix. Take one row and do the Gauss elimination. Okay? Now, before we do the examples, let's just write the equations so we here's a summary of the equations. Delta S is equal to R asterisk delta P, and this is equal to minus KSS inverse, KSP delta P. And then delta 0 is equal to R del P. And this is equal to R asterisk I del P. R transpose K and R. And then the last equation that we have here, this is equal to K delta over all, which is equal to F. I can put it in this form with the Gauss Elimination. Identity minus R asterisk 0 K reduced delta P delta S delta P 0. Thank you. Now this note on the energies. Of the original system or the full order system and the reduced order system. Okay, we said the potential energy of the full order is equal to 1/2 delta overall of the system transpose K of the entire system delta 0. I'm going to replace delta 0 from here. R delta P. This is R delta P, and then the delta transpose will be the transpose of this. So this will be 1/2 delta 0 transpose, R transpose. And then now, I'm going to replace this from here by the K reduced. So this will equal to 1/2 delta P transpose, K reduced, and delta P. And this says now that the potential energy of the full order system is equal to potential energy of the reduced order.
That's because nothing's changing in the secondary.
Pardon?
That's because nothing's changing in the secondary.
Because the secondary system is not excited directly, as we've seen for the control Q0 is not acting on the secondary system. Okay, now the kinetic energy, again of the full order, same story. I can write it down as 1/2 delta 0 transpose M delta 0. Put the same transformation, then we'll end up with delta P transpose R transpose M R delta primary, and I'm going to call this the reduced order mass matrix. So this will be, again, the kinetic energy of the reduced order. Now my system, which was originally M delta 0 double dot, K delta 0 is equal to F, reduced to M reduced delta P double dot, K reduced delta P is equal to Q P. Now this system, I can get the natural frequencies and the eigenvalues. The natural frequencies and corresponding eigenvectors. We can get this by, if this is single order, single degree of freedom system, and I want to get the natural frequency, this is a scalar equation. So I'll divide by m. So this will be k over m, which is omega squared. If it is matrix system, I'm going to invert this. So now I'm going to look at matrix A, which is m inverse k. This is for the full order. Or A, reduced order, m inverse r, kr. Okay, now I can do any eigenvalue problem, so I can extract the natural frequencies, the values and the corresponding eigenvectors, or can use MATLAB, so I can get the eigenvalues and the vectors using this command, EIG A full or EIG A reduced. Okay, now let's say this is 4 by 4 and I throw away 2 degrees as secondary, so this becomes 2 by 2. So here I'll have 4 eigenvalues and 4 by 4 matrices. Here I'll have 2 eigenvalues and 2 by 2 vectors. Okay. The vector 2 by 2, I can take it and bring it here. This is 2 by 2. This is 4 by 2. So I reconstruct the 4 by 1 eigenvector or the 4 by 4 eigenvector. So from the reduced eigenvector, I can reconstruct the entire mode shape of the structure. Okay, we'll do example on this. The important thing of what we've done is you have a complicated system. You see where you put the sensors and the actuators and the payload. These are the primary degrees of freedom. That's what you want to hold on, so you can get all the information about them. So you maintain them in this set of equations. The rest you can toss away for a while. You solve the eigenvalue problem. You do all your design with the reduced order system, and then once you're done with this system and you solve everything, you know how time response, you know the frequency response of the primary degrees of freedom, then you take them, expand them here to get what you have. Nothing is for free. Nothing is for free. The best thing is to work with this system, because everything is here. Once you reduce the order, then you will have some problems, as you will see. But for the low frequencies, everything is captured correctly. The high frequencies, you have distortions in them. Okay? So the name of the game is, you have complicated dynamic system, you reduce the order for the control purposes, so you have practical controller with small number of sensors and actuators, then you can implement it. During this process, you don't lose information, because I don't scratch rows and columns. I redesign the system to maintain the connectivity of the points. I maintain the energies of the system. When I do a controller design with Lyapunov, and I reduce the energy of the reduced order system, this means that I'm reducing the total kinetic energy and potential energy of the full order system. Okay, let's do an example.
it's sometimes a matter of discretion as to whether the degree of freedom will affect the potential energy. I mean, it has the ability to change the potential energy of the system. As a matter, I mean, sometimes that's a judgment call as to whether it's not necessarily, like a sign.
The controller. So look, you have in the notes that I gave you, you have this example. And you have to keep in mind for beam elements, we have the stiffness matrix is equal to EI over L cubed and then the rest is symmetric, and then the mass matrix is M L over 420, 156, 22L, 54, 13L, 156 minus 22L, and then 4 L squared. And then the same story, symmetric. So now we have our beam element. The example that we have EI is equal to 1. And then the length of each element is half meter. So you just plug in here. Plug in here. The mass per unit length is 1 kilogram per meter. So you plug here. So now for each element, we have this matrix. For each element, we have this matrix. Okay. Let me just take this out again. And now I have here two elements. Element 1 and 2. And then I have nodes connecting these two elements. This is node 1, 2, and 3. This has 2 degrees of freedom. V2, theta 2. This has V3, theta 3. Now when I write down the entire stiffness matrix, I'll take the element stiffness matrix, which is equal to 96, 24, minus 96, 24, 8, 4, 96, minus 24, and 8. And then here, 185, 0131, 0643, 0077. And then 0.0012, 0077, 0009, 2, then this last term, 1850. Now I'm going to describe the dynamics of the system, the static of the system, if you want to do the condensation. I'm sorry, I'm going to write both of them, the static and the dynamic. Let's look at the stiffness matrix, for example. I have here V1, theta 1, V2, theta 2, V3, theta 3. And then here is the force vector. Stiffness matrix, now we have 6 degrees of freedom. 2 are fixed and 4 are moving. So this should be 6 by 6. 1, 2, 3, 4, 5, and 6. Then the same story here. The first element is between node 1 and 2. And we always write the left degrees of freedom first. And then the right degrees of freedom second. So for this element, the description is right here. So I'm going to copy this here. So I have 96, 24, minus 96, and 24. And then this would be 24, 8 minus 24, and 4. Minus 24, and 8 minus 24, and 4, 96, minus 24, 24, and minus 96. So this is the first element. Stiffness matrix. Between 1 and 2. So we have 1 and 2. Now the second element is between 2 and 3. So it will extend between 2 and 3. 4 by 4. So this would be here. They are exactly the same. They are exactly the same. So I'm going to take this yellow block and slide it down until it fits on the blue block. Now when it fits on the blue block, I have 96 here and 96 here. So I have superposition. I have 24 here and I have minus 24 here. Superposition. And then I have minus 96 and 24. The second row, again I'm going to slide them. So 24 will come here. The 8, is that 24 or minus 24? It says minus 24 here. By symmetry. Okay, and then the 8 will come here. And then the remaining of the row, minus 24 and 4, minus 96, minus 24, 96, and minus 24. And then the last row is 24, 4, minus 24, and 8. The first element is between 1 and 2. It has nothing to do with 3. So everything here will be zeros. The second element between 2 and 3, it's not connected to 1. So everything here will be 0. Now the assembly of the stiffness matrix is now everything as it is except for the overlap zone where I have superposition of the elements. Now, after I'm done now from the assembly of the stiffness matrix, I'm going to impose the boundary condition. We said last lecture, the first thing we do is eliminate the column corresponding to the 0 degrees of freedom. So I'm going to eliminate this column. I'm going to eliminate theta 1 also because it is 0. So I'm going to eliminate its column. If we are not interested in the reaction, we're interested only in the deflections, then I'm going to eliminate also the rows corresponding to the 0 degrees of freedom. So I'm going to eliminate this row and this row. Now the final matrix will be I'm going to write it down here. (192) and then plus 24 and minus 24, it will be 0. Minus 96 and then 24. And then here is 0. It has to be symmetric. 16 minus 24 and 4. And then minus 96 minus 24, 96 minus 24. And then the last row, 24, 4 minus 24 and 8. So now, from the individual element, I assemble the overall matrix, impose the boundary condition, eliminate the columns corresponding to 0 degrees freedom, and also the rows. Then the reduced matrix is like this. Okay? So I'm going to write these matrices now. Now here is the full, I'm going to call this the full order system. So we have 192, 0, minus 96, and 24, and then 0, 16, minus 24, and 4, 96, minus 24, and 8. So this would be and then the same way we'll do it for the mass matrix. So when we do the mass matrix, it'll look like this. .3714, almost 0, 0. It's not 0, it's almost 0. By symmetry, so this would be 0, 4, 6, 4, 3, minus 0.0077, 7.0077, minus 0.01, and then minus 0.0049. So now my structure, if I model it by only 2 elements, that's what I call the full order system. That's my original system. So this has this mass matrix, and it has this stiffness matrix. For this system now, I take it to MATLAB and get the eigenvalues and the eigenvectors. M% K. So now you take the M inverse K, and now you will get these two matrices. The Eigenvector matrix is right here. The Eigenvalue matrix will be a diagonal matrix as the eigenvalues organized as omega squared in ascending order. I'm going to take the square root of this. This will give me the natural frequency, omega n, which is in radians per second. I'm going to convert it to hertz. Okay? Omega is equal to twice pi and f. So now I can calculate f by dividing over 2 pi. So this is 3.4. I'll divide it by 6 point something, so it will become 0.5 hertz, the first frequency. Second frequency, third frequency, and the fourth frequency. And then each one of these eigenvalues has corresponding eigenvector. The system matrices are 4 by 4. The eigenvector is 4 by 4. Okay? Now, our structure looks like this. This is node 2, node 3. If I have something hanging here and I have actuator and sensor at this location, then this is secondary for me. I'm going to eliminate the degrees of freedom of the secondary. So I'm going to define based on what I'm interested in. I'm interested in this location because everything is here. This is internal point. So I'm going to set it aside. So I'm going to define these two as delta secondary. These two, delta primary. Now I want to look only at the stiffness matrix because I'm going to do static condensation. So I'm going to look only at the stiffness matrix. Okay? So I'm going to take this stiffness matrix and do on it Gauss elimination. And then extract the R star and the K reduced. Now we'll say here, eliminate the secondary degrees of freedom, V2 and theta 2. So now I have 192, 0, 96, 24. And then 0, 16, minus 24. So this is the original system matrix. How I want to put this matrix, I have to put it in this form. One, one, 0, 0, 0, 0, 0, 0. And then here would be reduced. That's how I want it to look like. Because these 2 degrees of freedom are secondary. These 2 are primary. So I'm going to take the matrix and partition it, corresponding to 2 and 2. So these submatrices, this will be my KSS, KPP, and so on. I want to do Gauss reduction or Gauss elimination or rho reduction. So I have to make this identity. And then this is zeros and so on. So I'm going to come at the first element as my pivot element. I'm going to make it 1. And then eliminate the entire column. This, make it 1 and eliminate the entire column. Okay? There is no matrix inversion. So the first step, this will equal to 1 and then 0. This over this will be minus 0.5. This over this will be 0.125. So let me just take so we don't make mistakes. So this will be 0.125. This divide by 192. Then now I'm going to eliminate the entire column. This is very easy because it's already 0, so I don't have to do anything and the row will stay as it is. 16 minus 24 and 4. Now here I'm going to multiply by 1/2 and add. And add. Okay, so this will be 0. Of course here there's nothing will change because this is 0. And then 48 minus 12. And then the same story here, this will be 0, 4 minus 12, and 5. Now the second step, I'm going to pivot on this element. I'm going to make this 1, and then eliminate the entire column. This is my second pivot element. So now this will be 1, 0, minus 0.5 and 0.125. And then this is 0, and then this is 1 now. And this becomes minus 1.5 and 0.25. So I'm going to divide by 16. 24 over 16 is 1.5, and it is minus 4 over 16 is 0.25. And then do the same thing for the remaining elements. So this will be 12 minus 6 and 4. Now we're done because we put it in the canonical form, and this form says automatically this is minus r star, and then this is my k reduced. This k reduced is 12 minus 6 and 4. It is symmetric matrix. This matrix has no relation. If I do this, if I take the original system matrix and throw away the rows corresponding to delta S and the columns corresponding to delta S, the result is here. Has nothing to do with this. We did not throw away columns and rows. We used the connectivity and maintain it. Maintain the relationship between delta S and delta P and modify this matrix accordingly. So now this is my reduced order matrix. So this is now my KR. I can do the same for the mass matrix. I can do the same for the mass matrix. Or I can now take this R star, form the R matrix and calculate M. So this will be now here, 3 double dot, theta 3 double dot. And my M matrix. So,
you said I can do the same for the mass matrix. Does that mean that the R star that I'm going to get by reducing the K, the stiffness matrix, is the same.
No, we'll use this. This is my M. This would be R transpose M and R.
Yeah, and this R is the one that we got from reducing the stiffness.
Stiffness matrix.
We haven't done
Anything on the mass matrix. In the homework, I'll give you the dynamic condensation method. So you will see how this will be done. And you will see there is no difference. For the low frequencies, in the higher frequencies, you will see some modification. But for static condensation, I'll use everything from the stiffness matrix to generate my mass matrix. So now here I have R is now like this. .5 minus 0.25, and then 1.5 minus, I'm sorry, 0.25, and then 1, 0, 0, and 1. This is my R matrix. Minus R asterisk, so this would be 0.5 minus 0.125, 1.5 minus 0.25, and then I put the identity matrix, so this is my R. Right here. This is my R. So the mass matrix becomes like this. 7 minus 0.0524, 0.0095, and then this should be the same. Now I have M reduced and I have K reduced. Then I take these to MATLAB. And then get the V reduced, eigenvalue reduced, and this will be from the eigenvalue command of M inverse reduced, K reduced. Okay, again, this will be 2 eigenvalues. This will be eigenvector corresponding to these, so it will be 2 by 2. The matrices are 2 by 2, the eigenvalues and the eigenvectors 2 by 2 and 2 by 2. Now, we have E original, and we have V original. V original was 4 by 4. V reduced is 2 by 2. Now, I can extract the V original from R V reduced. Okay, because V reduced is 2 by 2. R is here. 4 rows and 2 columns. So this is 4 by 2. So the result will be here. V original, and this will be 4 by 2. I can get everything corresponding to the 2 frequencies that I extracted. So I'm not going to get the entire frequencies because my reduced order can only give me 2. So only 2 of these I can extract. But can I get all the deflection and all the points? Okay, now look at the results. We did the Gauss elimination. We got the reduced stiffness matrix. We got the transformation matrix R star. We extract from it the mass matrix. From these two, I go into MATLAB and calculate the natural frequencies. Now let's summarize what we have. Frequencies, .56, 3.34, I'm sorry, 54, and then 11.96, 34.72 hertz, and vector. Minus 0.1626, minus 0.557, minus 0.4788, minus 89, then I have two more like this. Now let's look at the reduced order. The first frequency is 0.56, exactly like this. Okay? The second frequency is 5.5, and this is 3.5. And this is always expected, always expected. If I have this system, these two frequencies are correct. These two frequencies are very bad. If I make the structure 3 elements, if I make the structure 3 elements, the only thing that will coincide and match these two. These two will be way off. Because I'm simplifying the system, the high frequencies are bad. Now I'm going to reduce it to become almost 1 element. So the first frequency will be correct, the second will be far off. The first frequency is exactly like this frequency. The second is way off. So if you reduce the order of the system, you have to keep in mind, reduce it so you have degrees of freedom twice as much as the modes that you want to control. At least twice as much as the modes that you want to control. If my system, I know, for example, a vibration mount, I want to design to isolate vibration from an engine to the floor. I know the frequencies of the engine. So I want to get the dynamics of the structure to be twice as much as this frequency. Twice as much as this frequency. So I know that when I sweep the vibration of the engine, I will only excite the frequencies that I have confidence in their values. The other frequencies are meaningless because I'm never going to excite them. The engine will never go to speeds higher than this. So these are mathematical numbers, meaningless. The only thing that I worry about is the frequencies that I'm going to excite. I have to have them correct. I have to have the control on it correct. So now, if I have system, I complicate it very much, I don't need all these, because all what I'm excited in this range. So I reduce the order, but my order has to be twice the highest frequency that I'm worried about. At least twice the highest frequency. Now, if you look at the eigenvector is here, 2 by 2. I'm going to take these and expand them. So I'm going to take this and multiply it by the R. So I can get the total vector. the total vector becomes like this. See what we have. The first set of numbers, all of them are the same sign. For the full order, all of them the same sign. Okay? They look different, but they are not. They look different, but they are very close. This number is 0.1626. This is 0.1926. The eigenvectors are not absolute, but they are relative. So now if I take this number, 0.1926, and make it 0.1626, the result will be like this. .126, 0.573, 496, 683. Because the value here is not absolute value. If I make this number 1 and I make this number 1, then I have normalized eigenvectors. So now if I change the number here to 0.126, then this is very close, this is very close, this is very close. Now look at the second eigenvector. Second eigenvector for the full order system changes polarity only once, from positive to negative. Always the case, always the case. This should change twice, this should change 3 times. Now this changes polarity one time. Look here. I have 2 half positive and then the other half is negative. Not like here. Here I have only 1/4 positive and then the rest is negative. Why? This is wrong already or very far. So this, I don't expect a miracle. This is also very far. But the first eigenvector and the eigenvalues are very close, So if you want good results or simple model, make your order reduction intelligently after you have some tea. So you can make your model very compatible to your practical application. That's enough for this, huh? So any questions? So we covered here, the first part that I did is the super important part, collocation of sensors and actuators. The second part is velocity feedback is very important because if you have collocated sensors and actuators, you have interlaced poles and zeros, you guarantee stability for any control gain. Then I did very simple finite element. The important part is what we've done last lecture, end of last lecture, and today is model order reduction. We have no time, so have a good evening. We'll see you on Wednesday. Homeworks. Anyone has homework not delivered? Okay, have a good evening. We'll see you then. I'll check so I'll know. Okay, goodbye. Topic which is optimal feedback, control, and in this chapter we will discuss the following methods: linear, quadratic, regulator, and we'll do 2 things here. Full state feedback and then output feedback. this is called LQR. And then I will do the linear quadratic Gaussian, and this is called LQG. And then I will do LQG slash LTR, and the LTR stands for loop transfer recovery. And then the last part that we will do here is the H infinity controller. In the first case here, there is no disturbance. And there is no disturbance on the structure or on the sensors. And we will show that this method is fantastic. But it's not practical, because this says here that we have to measure everything. If we have any structure, we have to know every state exactly. We have to measure position, velocity of every point on the structure. Okay? But once you say I have only limited number of sensors and actuators that I can put on the system, I can only use what I measure to do the control, then we lose the robustness. Then this system becomes, it can go unstable very easily, unless we are very careful. Okay? Now, we go in more realistic problem, where here we have disturbance on system and sensors, and also we have output feedback. So we have this case, output feedback. I should not say output feedback with limited number of sensors. And because we have limited number of sensors, we try to copy the full state feedback. And to do this, we will use Kalman filter along with it. And the Kalman filter is just a name that says I want to re-estimate what I'm not measuring. So I'm measuring only small number of pieces of information, and I want to reconstruct the system by using this Kalman filter, or just simple word, state estimator. I will not do state estimator here. I will not do state estimator here. Here I will use whatever I measure, I will use to do the control. Here we measure a small number of measurements, but we will construct the entire state vector using this Kalman filter. Kalman filter is the name associated with noisy sensors. So we have noisy sensor. If you don't have noise in the sensor, it has a different name. Okay? Anyway, we will not talk about the other type of state estimator. Now, once we do this, we have a system with noise, sensors with noise, and we have limited number of sensors, and we try to reconstruct the state, then we don't have any robust system anymore. We lose robustness. So this system, many people use it, but it has a lot of problems. Okay, and the main problem is not robust. And the word robust means accommodate, parameter, uncertainty, and can reject effect of external disturbances. This word means these two things. And you will see that in our derivation of this case, we will not consider anything of the disturbance of the system or the sensor. But in spite of this fact, you will see that this controller is very robust. Okay? But again, the main limitation, it's not practical because we have to measure everything. Okay? So just try it here, impractical. Okay. Now the last thing, this type of controller. Now, if we use this alone, we don't have robustness. I want to recover the robustness, so I have to add another attachment to it. It's called the loop transfer recovery. So this is robust. One more thing we want to add here is these three methods belong to one class. And this class is called H2 controllers. And we'll see where this name comes from. And then the last one that we will discuss is different class, and it's called H infinity controller. Here we try to look at the entire spectrum and make everything glow. Okay, so like we look at the area under certain curve and we try to make it low. Here we only look at the very high peaks and try to make them low. So this looks at the entire spectrum and try to make an area which is indicative of energy low. Here we look at the peaks and squeeze the peaks down. So this looks here at the maximum, and then here looks at areas or energies. Let's make it energy because you will see it in a few minutes. And then here look at the maximum energy. the derivations that like I will have, or you will have now in what I gave you, are very simple derivations. They don't have the time dependence, but they are rigorous derivations, so they are very useful. And you can look at any one of these areas, and again you can look at books written on any one of these. But we'll try to make it as simple and as direct to what we like it to be. And everything that we have here, we will do it by MATLAB Simulink. So you can run the simulation with Simulink. Okay, so I'll begin first by this first class of problems, the linear quadratic with full state feedback. This map has to be very clear here, very clear here. This is the best. This is the best. But the controller is more complicated, but it does everything that you want, especially for these two things. If I have disturbance at certain frequency range, I can shape my controller to reject this special frequency range. And this is very important in many applications. If you worry about certain range, I can shape my controller to go around this. If your structure varies with parameters with time, and I know roughly some bounds, how high, how low, the parameters can vary, then I can make my controller perform in these things. If you have, for example, rockets that have mass, and the mass is depleted as the rocket is launched, then this parameter uncertainty. Okay, the rocket is moving in Earth atmosphere and then moves outside the Earth atmosphere. The disturbance changes as you move along. I can make my controller work in all these different regimes if I design it properly. And the only tool that you can use to do all this, not the only tool, the most powerful tool is this. There is another tool which is not very popular. It's called the quantitative feedback theory. And only few people use it, and it's not very popular. But nonetheless, this is the most powerful tool that we'll have. Okay. All these are available in MATLAB as MATLAB commands, so you can use MATLAB directly. Again, we have the system dynamics. I'll give them like this. Some force. I can rewrite this system as we did, instead of second order differential equation. I'm going to write them as first order differential equation, and in state space. And to make this very general, as we did in, I'm going to make this B0. And that's where we place the forces. Now I can rewrite this in state space like this. I'll make this delta dot, delta double dot is equal to delta and delta dot this would be 0 and identity minus M inverse K, 0 and then M inverse 0 and 0. Or I can combine all this and call this x dot, and this I call it A. This is x. I call this B, and I'm going to call this U. So now we do the finite element, we generate the mass matrix and the stiffness matrix. We put the system in reduced order form. We reduce the order of the mass and the stiffness matrices, and then we generate the state space representation, which is this. So I'm going to just write next to this reduced order. So now this is the minimum configuration that I like to use to make my controller. So now here the system dynamics. Are given by x dot ax bu. The finite element size is half the size of the state space, because this is second order, this is first order. So I'm expanding the size. Okay. But now I deal with first order differential equation. I'm going to do the following controller. I'm going to generate this control efferent like this. And then I have negative feedback. So the x is usually n by 1. The a is n by n. So of course the x dot will be n by 1. The u, I can use many controllers. So I can make this m by 1. So accordingly the B matrix has to match the dimension, and then this would be n by m. The A is called the system matrix. The B is the input matrix. And then now the K is my control gain matrix. Now, if you look at the dimensions again, the x is n by 1. That's the state vector. The u, already we gave it a number of actuators. I have m actuators. So I have a vector of m. So now the k here will be m by n. Let me write down the combination of these two. First, the open loop system, which means there's no control. So from here, there's no control means the k is 0. This term will disappear, and the system equation is x dot ax. I'm going to close the loop now. Close the loop with negative feedback of every state in the system. Every state. I know everything. So now close loop. So I'm going to take this and plug it here. So the u becomes minus kx. We have x here and x here. I'll factor them out. And x dot will equal to a minus b k and x. Again, this a is n by n. And this a is the same story, n by n. Because the dimensions have to match. The open loop and the closed loop, they have the same size. So now, system matrices A or A minus BK, which I'm going to call it A closed loop X. These are matrices n by n, so they have how many eigenvalues? N. They have n eigenvalues. If the eigenvalues, all of them, are on the left-hand side plane, system is stable. If any one of the eigenvalues is on the right-hand side, the system is unstable. Now, A has very little damping, so the system eigenvalues are very close to the imaginary. My job here is to select the gain to make everything damped and damp it very fast. So I'm going to move the eigenvalues of A as much inside the left-hand side as I can. So I can dampen the system. Okay? So now our job is has to select the control gain matrix K to damp out the vibration. Okay. Now if I select K, how would I select it? Okay. All what I can select and have reasonable control over is the eigenvalues of the closed loop system. So I can specify, for example, the eigenvalues of the closed loop system. All what I can specify is n of them. So all the information that I have is n pieces of information. But now the gain matrix is m by n. It's not n. It is only n when the number of actuators is 1. So if I have freedom to place the eigenvalues in some place, I can only have n pieces of information. The unknowns are much higher, m by n. The unknowns are only n if I have single actuator. So if I have single actuator, every one of us can design this very fast. Everyone can design it very fast. You say, I'm going to put the eigenvalues here, that's a controller. But if I have m greater than 1, then I have the equations that I can generate much less than the number of unknowns. So now, we damp out the vibration. Okay, then the knowns are n, which is the number of eigenvalues. The unknowns are m by n, which are the coefficients of the K matrix. let me make this K. Like this, huh? This is different from the stiffness matrix, huh? This is the gain matrix. In the notes I had it smaller, lower case. Okay, this is the gain matrix. So now, if m is equal to 1, then this problem reduces to a very simple case called pole assignment or pole allocation method. If m is greater than 1, then let's just look at this example. I have more unknowns than equations. More unknowns than equations. So one example, for example, if I have z1 plus z2 is equal to 1. Okay. How many solutions we have? Infinite solution. So once we have infinite solution, it is not a deterministic problem anymore. This is a design problem. If I have the number of equations more than the number of unknowns, I have statistical problem. More equations than unknowns. So we have many test problems and we want to curve fit it with one parameter. For example, the stiffness of spring. So we tension it with one force and we measure the deflection. Tension it and measure the deflection. So I have many data and I have one parameter which is the stiffness. So I can curve fit it, get the stiffness. Our problem is different. Our problem, we have a small number of equations and many unknowns. So this is a design problem. So now, how would I select one solution out of all these solutions? I have infinite solutions. So I have to make a criteria and then see which solution has the best value of this criteria. And then I can extract it. So this becomes not only a design problem, but becomes optimum design problem. And that's where the need for this is essential. We have to have an optimization so we can get the best combination of these solutions that will have the highest merit value that we assign. We will say, I like, my objective is to do this. Then whatever design that will have the highest merit, then we will select it. And each one of us will have different objective. Each one of us will have his own design. Exactly like the cars. One objective is to have minimum fuel consumption, so you get a VW bug. Or you don't care about fuel consumption, so you get Marquis like Mario. Huh? Marquis Grand with 8 cylinders and how many horsepower? 500 horsepower. So every one of us has his own design objective. Okay? So now, what is the... So now we have to put a performance index. And it's called the J. And this is called also figure of merit. Objective function and so on. In control theories, performance index is very common, and this performance index has several things. The first thing is system energy. But if I leave it system energy alone, it will be a horrible controller. If I want to lower the system energy alone, I can put infinite horsepower to stop any structure from moving. Any structure, I can make it stop immediately if I have infinite horsepower to do it. So this is not the only way. So if I want to measure my controller in a better way, I want to drop the system energy, but at the same time, I don't want to pay too much to do the controller. So now, I'm going to add to it the control energy. Problem now is this system is time dependent, moves with time. So I want to drop the system energy as soon as I can in the shorter period of time. So now I have to do this over a period of time. And I want to look at the integration of the energy over time. So now I want to drop both of them as soon as I can in the shortest period of time. I don't want to drop this alone and pay a lot of money for the control energy. If I do, then this will be high, this will be low, the sum will be high. So now I try to find a better solution until I bring both of them to within reason. Now one of us will say system energy is very important to me. One will say, no, I don't want to pay too much money. Exactly the same like the car simulation. Car simulation, that's the energy that you pay. This may be comfort level. You're comfortable in this VW, or you want to get a much more comfortable car, but then you will pay for it energy. So each one of us will put emphasis on which of these is important. And then we will translate this into equation form now. Integral from 0 to infinity. System energy. The system has displacement and velocity. So now I'm going to make the energy, kinetic energy and potential energy. X and X transpose. And then in between them, I put a weighting matrix, Q. This matrix can be any matrix that you select. We can select this matrix to be the mass and the stiffness. So the multiplication will be the sum of kinetic energy and potential energy. But also you can select anything you want. For example, you have like the platform, station, space station. Some locations are very important than other locations. So I can, from this vector, I can say the location that's very important, put on it big weight. Penalty. Location is not important, I relax the weight on it. So I have a lot of freedom in this. This is your choosing. And then, same for the control energy. I'm going to put it like this, U and U transpose, and then R and dt. So if you look at the first part, this can be kinetic energy and potential energy. This is the system energy. The control energy is done in this form. Each one of them look U squared and X squared. So each one of them is quadratic. Oops, and we erased the name of the title, which is the linear quadratic. Okay? That's what we want to do now. So the name linear comes from here. This is a linear system. Quadratic, because my energies are put in quadratic form. Everything is quadratic. And the reason you get very nice optimum. So if you have quadratic equations, then you have unique optimum, global optimum. Okay? Now the last word is the regulator. In vibration, we want to keep the vibration 0. After some period of time, we want to keep it to 0. In robots, I don't want to keep the robot at 0, because if it's at 0, it will not move. In the robot, for example, if I'm using it to track a weld, I put a torch at the end of the robot, I want to track a weld, I want to use linear quadratic tracker. The weld is not 0. The weld is not all at one place, but the weld has profile, and I want to track it. The regulator, I want to make everything 0. As soon as possible, make this 0. Now, for example, if you drive a car, you are a linear quadratic tracker, because you come and you want to turn here. You don't want to turn after you pass the intersection and then you turn here, because that's the controller does like this. If I have error which is more in one direction, then I turn. If it is in the other direction, I turn in the opposite direction. That's the controller. Here, when I have error in the opposite direction, I turn. If I want to go now and drive in a street and then I want to turn here, I am tracking the street. So I come close to here and then I turn next to it. Okay, so for example, if you have on the road something like this, step. Okay, you don't want to go and then hit the step and trip over the step, because you will not see the step as long as I am moving here. Because the error here is 0, 0, 0, 0 until I hit this point. When I hit this point, I have this much error. So I have to lift my foot. Okay? So now the tracking system, what it does, it makes you get ready. Before you hit the step, you move your foot up. So you can track the profile of the road. Same as the welding, I have to track the profile of the welding, not overshoot and then come back again. In our case, we want everything to be 0. If I have any error, positive or negative, make it 0. So that's the distinction, and all the things that we will do, we'll try to make it 0. The tracker has completely different theory. Okay. So the regulator is to make x is 0, and then quadratic because of j, linear because of x dot bu. Okay, so now we have everything here in this performance index. Then we just say here condition of we'll see here the system is stable if there is a positive effect symmetric, and then in this class I'm going to say also time invariant matrix P satisfying d by dt x transpose P x is equal to minus a Q x. And again, you can look at this as we did a couple lectures ago, and it was in the homework, that this defines some Lyapunov function, which is positive definite function. So if I make the energy decay of this function strictly negative, because the term between brackets, this is squared, and the Q, which I did not talk about, and the R, which I did not talk about, these two are also positive definite matrices. This is x squared, so all these are positive, and then we have negative, so the energy of the system is decaying negatively. So before we do this, we want to put here two things. And these two are positive definite symmetric matrices. The reason for this to be positive definite, it has mass matrix, for example, and has stiffness matrix. Both of them are positive matrices. So, and again, both of them, for any structure that we are selecting, have symmetry. Okay, have symmetry.
Dr.
Okay.
Rob, does that also imply that it has a minimum? Like it's concave up?
Yes, sir. This automatically will give you one single. This objective function has one single minimum. One single minimum. So this makes the quadratic optimization is very nice, and we'll have one single solution. The only thing that varies, you selected this, you selected this. And every one of us can select different value. Okay? So, okay. So now the proof of this. I'll take the equation again that we have, d by dt, x transpose p and x, and then differentiate. So this will be x transpose p and x transpose p and x dot, and replace the x dot from the equation. And the equation now will be the bottom equation when we have the closed loop system. So I replace x dot by a minus bk transpose p and x, p a minus bk. And then now we'll expand and organize. So I'm going to make this a closed loop transpose p and x plus. I'm sorry. We have the x here, so the x has to be and then this second term, we have x transpose p, and then a c, and x and x. So now this I can rewrite it down as x transpose a c transpose p plus p a c and x. Now then here it says that d by dt x transpose p and x is equal to x transpose AC transpose p plus p AC and x. Okay. If this is equal to minus x transpose q plus A transpose and x, this means that we have AC transpose P plus P AC is equal to minus, okay. Now Q is positive definite, R is positive definite. K transpose K is K squared times positive plus positive, everything is positive, and then negative. This means that this is equal to minus a big positive definite matrix. What this equation says now, if we have this, then AC is stable, because this is Lyapunov equation. And this says now, then this will be the condition that have AC stable. Now let's go and say one thing. If K is 0, so this means that we have open loop. And we look at what we have here. I'm going to drop from all this the K. I'm going to drop the K. Okay, and the AC becomes A. The right hand side, this will drop and it becomes minus Q. So this again says the open loop system is stable. Now I'm going to calculate the value of the performance index now. This equation, if I have a matrix A and I give any Q, I can calculate P. Okay, and you can go into MATLAB and then use this command, Lyapunov command. Lyapunov command, you give A and Q. And then this will give me the solution of Lyapunov equation, which is the P. So you just say help. So you get how to solve this equation. Okay. I'm gonna leave this equation for a while. We don't need all this. look at the performance index. Read this also. I need it. Okay, I'll write it here. We have J is equal to also here in the performance index, I did not put another term here. There's another term that they usually put here. If they are, for example, targeting an object. So for example, you have the shuttle is trying to dock with the space station. Okay, so both of them, they have to be at the same time at the same location. You don't want the shuttle to hit this or vice versa, or there will be a gap between them. So you want both of them at certain instant of time to match exactly. So usually the performance index has some term to define the rendezvousing type problem. If you want to rendezvous with an object, you have to be at the same place at the same time. In vibration, we want to rendezvous with the zero. Everything is the zero. So this is all gone. Okay? So that's what makes life much easier. Also, you will see, and when you look at MATLAB, you will see there is another term here, cross-coupling between the U and the X. We don't want any cross-coupling. We want simple, linear, quadratic regulator. Okay? So my performance index is very simple. Have X transpose, Q and X. And then now I'm going to replace the U from here. So this becomes X transpose. Of course, we have negative for this U and negative for this U. They become positive. And I have X transpose, K transpose, and then I have R, and then I have K, and then I have X. And then dt. And then now I'll group these. So now this will be 1/2 integral X transpose dt. Now if you look at this term and you look at this term, they are exactly the same. Now if I want my linear quadratic regulator to give me a controller that is stable, then I better select this equal to the negative of this. That's the most powerful thing in linear quadratic regulator. If you take the equation of the performance index and you take the result that we will extract, how much is the control gain, automatically, without thinking, this is a stable controller. Why? Because we found the condition for stability, and I'm going to use this as we drive the controller later on. So now this term, I'm going to replace it by minus what we have here. So this will equal to now I have the integration of the differentiation, so the result will be just the value that we have, and I put the limits on it. So this is 1/2 again, the controller that I'm selecting it to be stable. So at time equals infinity, I should not have any vibration. So this term should go to 0. And the performance index now reduces to this simple equation. Depending on your initial displacement from the equilibrium, the energy of the system at this location is indicative of my performance index. Okay, now we don't need all this. Now the design problem becomes find the control gain matrix K to minimize J, which we wrote it as an integral, but not anymore. J is just a scalar value now, 1/2 x transpose 0 p x of 0. This problem is unconstrained. And that's what I'll solve in this class. You don't have any constraints on the control energy. So for example, if this comes up with control gain K, when you multiply it by the X, will give you a force U, for example, 10 pounds, and your actuator can give you 1 pound, it's too bad. The only thing that you have to do, change the R. Put penalty on the R. So make this, I want to pay very small control effort. So I want to make more penalty on the control effort. So I have to make R large. So I'll bring the U down. Okay, this is one way of getting around this, but there are techniques to put constraint on the U. I'll say here, U should be less than certain number. Okay, but this problem is unconstrained optimization. So now has the optimum when goes to 0. But in this formulation, it looks like J does not depend on K. J depends only on P. Okay? But P from here depends on K. So now I can differentiate partially with respect to P, and then differentiate P partially with respect to K, and then get the final result. Okay? Or I can do something like this. I want to get the variation of J is equal to 0, which is equivalent to 1/2 x transpose 0, the variation of P, capital P, is equal to 0. Okay? Now, I'm going to get the variation of P in terms of variation of K from here. So now, I can take, but this equation, I have to be careful because AC has K inside it. So I'm going to expand this equation. I will say here, but AC transpose P, AC is equal to minus or this will be A minus BK transpose P is equal to minus. Then then I'm going to get the variations now. I have two functions. I'm going to differentiate them. So I'm going to get the first, A minus bk transpose del p plus del p A minus bk. And then I'm going to get the variation with respect to k. So now this will be k transpose del k transpose b transpose p. And then here minus b del k. And the right hand side, this does not depend on either one of them, so this goes to 0. And then this will be rk minus k transpose r del k. Okay. The first term, the second term, if you look at this term, I'm going to leave it like it is, dp del k. And this term looks like this if I put transpose on it. So it will be p b del k transpose. The last term, I'm going to bring it to the right hand side, so it becomes k transpose r del k. Okay, and then this term looks like it if I take the transpose of it. So this will be k transpose r. In all these, the r and the p, because they are symmetric, I don't put transpose on them because the transpose will be the same. So this will be, and del k is equal to 0. Now if you look at what we have here, only two terms have del p in it. The remaining terms have del k in it. Okay? I want del j to equal 0. Del j to be equal to 0, this and this are not 0. So it requires del p is equal to 0. How can I make del p is equal to 0 here? If I make the box, the brown box is 0. If I make the brown box is 0. I can make the brown box is 0. This is negative, this is positive. This is exactly this. This is exactly this. So if I make bp is equal to k transpose r, then all this box will go to 0. This is not 0. This is not 0, so del p will equal to 0. So now here, del p is equal to 0 when pb is equal to k transpose r. Or I'm interested in k. Or I can transpose this, so this will be b transpose p is equal to r and k. Or k is equal to r inverse b transpose p. So now, if I want to calculate the gain of the optimal LQR controller, I have the R. I put the R, the weighting matrix for the control effort. I know the B. I have to get this P. How would I get this? I get it from here. But to get it from here, I need the gain. Okay? So this is like which one comes first. So now I'm going to take this and combine them and come up with very beautiful equation, which is very famous equation. Then now as A minus B K transpose P, I'm sorry, P A minus BK is equal to minus Q minus K transpose R K, replace K by R inverse B transpose P. I'm going to plug every K and replace it by what we have here. So we have the first term here will be A transpose P. And then I have minus K transpose B transpose P. I'm going to replace the K by what we have here. So this is R inverse B transpose, and then we have, this is K transpose, I'm sorry. Would be K transpose, so we have to have here P, and then B, and then R inverse. Okay, and then plus P, A. And then this term will be minus P, B, and then I replace the K from here. So this would be R inverse P transpose P. So now we're done from these four terms. And this should equal to minus Q minus R, and then K is R inverse B transpose P. K transpose will be the flip over of this, so this will be P, B, and R inverse. Now look at what we have here now. These two will be identity matrix. We have P, B, R inverse, P transpose P, which is equal to one of these. So I'm going to cancel one of these with this. Now we have beautiful equation. The equation is A transpose P, P A minus PB R inverse P transpose P is equal to minus Q. This equation is very famous, and it's called the Riccati Equation. Now, I have the A of the open loop. I have the B of the open loop. I have the weights of the state vector. I have the weights of the control effort. We have, of course, the B. The only unknown now, P and P here linear, but unfortunately, P and P here are nonlinear. This is P squared and then P. So this equation is nonlinear equation, but the solution is very trivial. We go in MATLAB, and say now get me the gain K equal to this command. LQR, linear quadratic Gaussian, linear quadratic regulator, and then give it the A, the B, the Q, and the R. Okay? And the solution will give you the gain, and if I want more information about the P, then I can also come here and put the P and the K in between square brackets. then you get the solution. Next time I'm going to show how to solve this in a very simple way, so we can compare the simple way, which is the Hamiltonian matrix, with the linear quadratic regulator. It's enough. You took 4 minutes more than your time, so we'll have a good weekend, and we'll see you next week. K will be m by n. And we said if the number of actuators is equal to 1, then we have deterministic route. By that we say I can place the eigenvalues of the closed loop in any particular place. I have n of these eigenvalues. Then I can solve for n unknowns, which are the coefficients of the K matrix, the gain matrix. Then placing the eigenvalues of A minus B K in any desired place, I can extract the n unknowns at desired locations. This will give us n equations. Then we can solve for the n unknowns. The n unknown coefficients of the gain matrix K. If m is not equal to 1, then we have more unknowns than equation, and we have to use optimum control. Infinite solution. Then use optimum control. And then we said now we define the performance index. J, and this J has penalty on the states of the system as well as of the control effort on the system. And we'll put this 1/2, and then we will select weighting matrices Q and R. And what we said last lecture, that these matrices are positive, indefinite, and symmetric. I showed for stable closed loop, we showed that there is a P matrix such that d by dt x transpose px is equal to minus q plus k transpose rk and then use the stability condition for the LQR along with the performance index. Then this gives us J is equal to 1/2 X naught, and then J is optimal when the variation del J is equal to 0, or this is equivalent to del P is also equal to 0. And from this condition, then this gave us the very famous equation A transpose P plus P and A minus P transpose which we call it the Riccati equation. And so that's the first thing that we said, the system equation looks like this. The need for optimal control and the performance index. Now number 3, the stability condition for the LQR, and when we augment it with the J and get the optimality conditions, then the result is this last 2 equations. That's where we stop. Now, I have the open loop matrix, A. I have the input matrix, B, where the actuators are located. The sensors everywhere. The sensors everywhere. We measure all the state vector. And the LQR is all X are available or accessible. All the entire state vector is accessible. And this controller is called full state feedback. And the feedback is because of this sign. I'm feeding this negatively back. Okay. So now we have the A, the B, and then now, as a designer, you select these two matrices, the R and the Q. How much each state is important than the other, how much is the control effort is important than the vibration. This is vibration, this is energy to control the vibration. So now we have the Q, we have the B, we have the R, we have the A. The only unknown in this quadratic equation is the P. Solve for the P. Once we have the P, then we take it, multiply it times this, we can calculate the gain K. Okay? The important thing is, whatever controller that you will get will always be stable. Will always be stable. Blindly, it is a stable controller. Because we used this condition to find the optimum condition for the controller. Okay? So this is one way of solving this. And the solution for the control gain K, solve Riccati for P. There's two ways that I put in the notes for solving it. Okay? To solve this, now the easy way is the LQR command, A, B, Q, and R, and then I can extract from here two things, the gain and P. Number A. Number B, which I will not explain in the class, but you have it in the note for the sake of completion, is the using the eigen structure of a particular matrix called the Hamiltonian Matrix. This matrix A has a special structure that we will use quite extensively in the H infinity controller. It has the A and the minus B transpose R. So the mistakes. BR inverse B transpose minus A transpose and minus Q. And we'll use this particular eigenstructure, so we'll extract from here the eigenvalues of H, and we'll see that these come in pairs. One is stable, one is unstable. We'll get the eigenvectors corresponding to the stable eigenvalue, and then from it we can generate the P. So P equal to W21, W11 inverse, where the W is the eigenvector matrix. And these are the eigenvectors corresponding to the stable eigenvalues of H. I give the proof. The proof is very easy, but we don't have time to go over it. Okay? So we can use either one of these two, but this is using this approach to calculate the K and the P. Okay, so now we calculate the gain. I'm going to use the gain to do some calculation of system response and so on. And we'll do this by an example. And the example that we will have spring mass system that has M of unity, stiffness of unity, damping coefficient of unity. So now we have system. You make this delta. And the delta double dot, C delta dot, A delta is equal to the control force, U. And I'll put this in state space, and I'll plug in the M and the C and the K, so this becomes 1, 1, and 1. And the state space equation will be delta dot, delta double dot, or x dot equal to 0, 1, minus 1, minus 1 times x plus C, then the 0 and 1. This is our A matrix and the B matrix of the system. So now I'll use Q 1001. U, oops. I have to start again from 0, Dr. Han. Go again, both of them. Okay, so we have Q will equal to 0. And then we have the controller is a single controller. So I'll have R is a scalar. Now we have the A, the B, the Q, and the R. So now we can plug in this equation, calculate the gain. If we just want to calculate the gain only, then you can just say LQR, A, B, Q, and R. If you just say this, the output will be just the control gain K. And if you do this, then this will be 0.4143 and 0.6168, I think. 0.6819. Okay. Now your controller will be like this. Your controller will be like this. So now you can look at any system disturbance that acts on the system, and then apply the controller and look how the response will be, how the system response will be when you put the controller and without the controller. I'm going to show you this with Simulink. So you can do Simulink is very important as we go at the end of the class, where we will use this with D-space so we can control real structure. All the machines should have Simulink on it. Let's turn one light off. Keep the back lit so no one will sleep. Okay, so this is our MATLAB. This is your setting. Okay, so now this is our Simulink box, this little card. And then you have here the things that we can do, and we will we'll do the neural network and then the fuzzy logic, also toolboxes. Okay, so we'll begin with the Simulink, and then it has many pull-down menus. So we have continuous systems and discrete systems. So if you are doing digital controller, you can also design it here. You have functions and then math. You can do nonlinear systems. You can do signal processing, and then you can generate things that you send to oscilloscope, for example, or any other things that we can use, and we'll use, for example, the MATLAB main notebook as a sink also. So you can dump the data on it in a data file, and then we can use it and plot several things together. And then the sources, if you want to excite the system sinusoidally, random, and so on, and so step inputs and so on. So you can do many of these. So I'm going to start first with the continuous system. Continuous system has many of these things: derivative, integral, memory, state space, transfer function, and so on. So I'm using in my representation here state space. So I'm going to go to the state space. Let me just first make a worksheet so we can do things in it. Okay? And then I'll go into the state space and then put it here in my work space. Now here I can expand this and move it around and so on. This has the A and the B and the C and the D. Okay? Now I'm going and click on it. So now it says what is the A, what's the B, what is the C and the D, and the initial condition that you have on the system. Okay? So now my A is right here, the B is here, and then the C is everything, I measure everything, and the D, I don't have any cross-coupling between the U and the output. Okay? So now we'll update what we have here, exactly like what you do with MATLAB. So I'll put 1, and then semicolon, -1, and -1. So this is the A matrix. The B matrix is 0 and 1, and then now it is a vector, so I'll put the transpose on it. Okay, and then the C, I can write it identity matrix, or I'll make it I, 2. So this is the C, and then the D matrix is has to be 0, and then we have to put the right dimensions because the output is 2 by 1, so I have to make the D a vector like this. So when I multiply it by the single input, I maintain the dimensionality on the two sides. And then now the initial condition for the spring mass system, I'm just going to pull it, for example, in one direction, and keep it constant with 0 velocity, and then let go, and then see what will happen. So the initial condition, I have vector 2 by 1, so I'm going to put 1, and then 0, and then a vector, I put the transpose on it. So now we're done. If you make any mistake here, we'll tell you where the mistake was. If you did not put the right D and so on, then we'll give you the response on it, okay? We can do a lot of things with this, with the format command. We can flip over and so on. We can change the background color to any color we want and so on. This is horrible color, so we just make it... Okay, we'll leave it like it is white. Okay? So now we want to have here the controller. The controller is represented by this block. Okay? So I have to put a gain matrix. So now I look at the math, and then the math has many things. Okay? It has gain, but it has also a matrix gain here. I need the matrix gain, because this gain is a single number. It's a single number. This matrix gain, many numbers. So I'm going to take this matrix gain and then pull it here. Okay? I'm going to make another one here and then just pull it here. And we'll see in 1 minute what will happen. Okay? Now, I want to connect this to this. You will see on every block it has an in arrow and an out arrow. So I want to connect this to this. But these two are in. So I cannot connect these two. So I have to flip this to make connection between out arrow and in arrow. So I come here, you mark the block, and then you go to the format. And the format, it says flip the block. So you can flip it. So now the output arrow here and the input arrow here. So now I can connect these two easy. You just go in and then drag the mouse. Oops, I'm sorry. to here. Oops. Okay, and then we clean it like this. Okay, so now we have connection between this gain matrix and this block. Now this gain matrix, I have to put the numbers that we have it from here. Okay, so now I go in this gain matrix, let me just move it here. Okay, and then now I go in and double click on it. Double click, it says here what are the numbers. These are some previous examples. So now we have to clean it. I'll remove all this and then put the new numbers. 0.4134 or 143, I think, and then 0.6819. Now this matrix is M by N. So it is M is equal to 1, so it is a row, 1 by 2. So this is correct, I don't need the transpose. So this is done. Now if we want to run this for the uncontrolled case, I'll just put these two numbers, 0 and 0. 0 and 0. So now we're done from this. Okay, now I'm going to take the output from here and connect it to this. Okay, and then we'll just lift to this so the lines will be straight. And the output from here is my entire X vector. The input here is my control action U. So my control action will go here. I just want to make one thing here. I go here and make this whole thing negative. Okay, so this would be negative feedback. And this is negative also. Okay, now I'm going to take the X vector and bring it to here, multiply it by K, and then negatively feed it back to the top. Because here I had to put the negative in the gain, because I don't have a summing junction in this system. So now we have to take from here, I go like this, and then we feed this back. Now at this location I have my entire X vector. I cannot plot everything at the same time, so I have to select what I want to plot. So from here, I'm going to make this my C matrix. I'm going to measure only, for example, one parameter and display it on a scope. So this K, I can select it as I want. So for example here, I'm going to select it as 1 and 0. So I'm going to only, from this entire X, I'm going to show the displacement. Okay, I can repeat this next to it, and I make the K 0 and 1. Then I can show the velocity. Then I can show both of them. But I'm not going to do this now, but you can do it later on. So now what is left now? What we're going to see? What we're going to see? So I have to go in the main menu of Simulink and then look at the sinks. So the sink I can display on a graph, display on a scope, or send to my workplace on MATLAB. I'm going to do both of these. So I'm going to take the scope and put it here. And then I'm going to take the workspace and put it here. So whatever we will get out from here, which is the displacement, I'm going to send it on the scope and on the workspace. So from the workspace, and then from here to here. In the handout that I gave you, I only gave you the scope. I did not put this. But this is very important if you want to do any changes that you like to have, like if you have many runs and then you want to collect them all in a data file and then you can plot each one against the other and so on and so forth. Okay, so now the workspace, I have to define what I'm going to measure. This is the variable name, simulation output. I'm going to remove this and make it x1. which is the displacement. Okay, the maximum number of rows here is 1,000, infinite. I'm going to make it 500, 1,000, and so on. Because infinite will take the whole computer and never get done. So now this will make it 1,000 points. And then I'm going to make the sample interval 0.01 second. And then now you want to save it in whatever format. I'm going to save it in a matrix form. And then once I run the program, the output will be under this name. And if I take the size will be 1,000 data points. Then we say OK. Now we're ready to run. So when you run, you say now the simulation. You can look at the parameters, or you can leave them as the default values. It will have automatic step size for integration, and it is using OD 45. And then I'm going to start the integration process. Oops. What did we do? Untitled. Port to mismatch, output port and what is a width of 2 output port. See the one that I saved, open. This is the color. This is color. Simulation. Run. See, like this is the scope. You have to see what did you do wrong. So we start from 1, and then this is the uncontrolled where I have the gain. It's 0 and 0. Now we can also look at here in the main worksheet. And we have, for example, I can plot the x1 and then this would be the response. So we have, for example, if I run this again with the controller on, I can save the data and plot both of them simultaneously. So, so we can go here, for example, and save x1 uncontrolled is equal to x1. And then now we go back again to the LQR model, and then we go in the gain and then change the gain matrix. So this would be 0.4143, and then 0.6819, and then save, and then and run. So now this is done. And then we can see the scope. You could see the, when you put the controller on, like it is almost like critically damp the response. And then we also have the response here. If we go to and this would be the response of the controller. Now I saved this, and I have this. Then I can plot both of them simultaneously on the same plot. But we have to make, for example, the number of points. Ij is equal to 1 to 1000. That's the data points. And then we have the time of Ij is equal to 0.01, the step size, times, and then end. And then we can plot time and x1 uncontrolled, and for example we'll make it red, and time x1 blue, the controlled, and then we put the grid. And that's what you have in your handout that I gave you. So we have both of them on the same plot. So we can could see the one with the optimum controller and the one without any control. The one without any control has a lot of damping. The damping here is almost 0.5. The zeta is 0.5, so it's very high damping. So that's why we have this overshoot. But in most systems, we don't have any damping here. So this is very light damping, and the system will keep oscillating. When you put the controller on, then the controller will level it off very fast. Okay? So now, Simulink has a lot of nice features, and we'll use it quite a bit in the linear quadratic Gaussian controller and the LQG, LTR, and H infinity, and also in the fuzzy logic and neural control. Okay? Get off this. This part will do the phase, and the main purpose of this, we want to show that the phase margin greater than or equal to 60 degree, and the gain margin is infinite. That's for the LQR. Now, the phase margin is called PM. The gain margin is GM. First is what are the gain margin and phase. So if we have here real axis and imaginary axis, and then I plot the G, H of a system like this. If I plot these like this, then the G and H are function of the Laplace operator S of the Laplace complex number. And I can replace the Laplace by G omega, and the result will be G and H, both of them function of omega. And because we have imaginary number, then this will give us real part and imaginary part. So for any frequency, I can plot the real and imaginary against each other. And the result will be nitrogen plot. Okay. Now, but we have to keep in mind that the transfer function of this system, this is, for example, the output and input for a negative feedback. So we have the output over the reference command is equal to and this will say that the characteristic equation should equal to 0 and GH is equal to minus 1.
Excuse me, no H on the numerator, I think.
Ah, I'm sorry. Okay, so now we have GH will equal to minus 1. Okay, so this says that the magnitude 1, and the phase angle is 180 degree. When I have this is equal to 0, it means I have the characteristic equation, and it means the denominator will be 0, everything will blow up, and the system will become unstable, on the verge of blowing up, and the amplitude will be infinite. Okay? I don't want the amplitude to be infinite. Okay? So I want to stay as far as I can from point minus 1. Now, if my system has this characteristic, and this characteristic intersects at this location, I'll call this distance little a. Now the h here or here takes the displacement or velocity of the system, multiply it, and feed it back. So we've seen in LQR, this H has the control gain matrix. If I make this matrix big, then what I feed back is big. And when I have here H is big, the result will be like this. And then when I increase it more, the result will be like this. And when I increase it more, it will intersect at this point and the system will blow up. So now, if I am at this location, what is my gain margin that I can pump in the system without making it unstable? So the gain margin will equal to 1 over A. 1 over A. Okay, so physically, the gain margin, is how much additional gain I can put in the system before I bring it to the instability point. So the gain margin now is the gain multiplier that will bring the system to instability limit. Now also, if you look here, the phase angle of the GH will be 180 degree if I hit the infinite deflection limit. So this is the phase angle when I come very close to the limit of instability. Now, if I want to keep as close as possible to the maximum limit of the gain, then I want the amplitude to be as close as possible to 1. So let me make here from here a circle, like this. This circle is a unit circle. So if I keep pumping the amplitude until I bring it very close to the limit that will make me at -1, I want to see how much the phase will be. So from this drawing, this is my GH characteristic. This is the amplitude that corresponds to the maximum gain that I can put in the system. So the phase now will be like this. And my phase margin is this angle. I am operating at this point. I am far away from the phase that will make me unstable. So the difference is my phase margin. Now we want to show if I use this LQR that we have, I will have very large distance between me and becoming unstable, both in the phase and in the gain. In the gain it says you can put any gain that you want, and the system will never go unstable. Why? Because we will see that we are very far away always from this point. I'll never come close to this point. Everything will lie away from this point. Okay, now we will prove this, and we'll also show it by an example. Please circulate this. Here we go.
The origin to where the unit circle hits the system, the yellow dot.
Okay.
That line there, that's the reference that you measured the phase marking from? So you put another,
No, this is my characteristic at any frequency.
Right.
At any frequency. Okay. I want to give this system the maximum gain possible that will just make me unstable, which means that I have to have the amplitude of unity. Okay. Now I want to see how much is the phase. So the unit circle is the locus of all points that have the maximum gain margin of 1. The maximum amplitude of 1. Now when these two lines intersect, that would be my operating frequency. Because at this point, if I am at this location, then that's my phase margin. I'm sorry, that's my phase angle. Okay, this is my phase angle. If I am at this location, this is my phase angle. Okay, and the phase angle is defined between the real and imaginary parts of the GH. So this is my operating point, and this would be how far I am from just becoming unstable. Now we need a couple of things. First thing is we have x dot is equal to ax plus bu. So now in the Laplace domain, the x dot will be s cap x of s, and then this would be a x of s plus b cap u of s. And then now I can group the x's in one side. So I have si minus a x of s is equal to b u of s. And then the transfer function x of x over u, this will equal to s I minus b, minus a inverse and b. This is n by n, multiplying the x vector, which is n by 1. So now this result is n by 1. So now if I factor out the x outside, this is n by n. The Laplace is a scalar. So to make the units uniform, I have to put identity matrix, which is n by n. So now everything will be on this side is n by n. So now this is a square matrix. I can invert it and get the transfer function of the system I, okay? Now we'll come at as A transpose P plus P, A Riccati equation minus P B or inverse B equal to minus Q. Then now I can take this equation and replace it like this. Make it minus A transpose P minus PA plus PB or inverse B transpose P. And I bring this here will be minus Q is equal to 0. This is the Riccati equation. And then I'll just add and subtract. Laplace P to this equation. And I'll add them here and subtract them from here. So now we'll have P SI minus A, which is this term, minus SI minus A, and the whole thing is transposed here, and P, and then P, B, or inverse B transpose P minus Q is equal to 0. Now I'll pre-multiply and post-multiply. By these two matrices, B transpose SI minus A inverse and transpose an inverse and minus SI minus A inverse and B. Now, also, so the result will be like this. B transpose minus SI minus A transpose inverse, then P and B, B transpose P, SI minus A inverse and B, plus B transpose minus SI minus A transpose P, B, or inverse B, P, then SI minus A inverse and B, and this whole thing will equal to B transpose minus SI minus A transpose inverse Q minus B. And then here I'll replace the gain I replace each VE. R inverse P transpose P by gain K. And also, so this equation reduces to the following. Do just some manipulation, and this becomes I plus B transpose minus SI minus A transpose inverse A transpose, and then R I plus K SI minus A inverse and B, and then equals to R plus minus SI minus A transpose inverse Q SI minus A inverse and B. Moving from here to here, we added an R, which is I times R times I, and subtract R. So we did not do anything to the equation. Okay? Now we come and say all this is positive number. This is positive definite. This and this is transpose. These are two are the transpose. Transpose, you look at the T here and here. This is the transpose of the complex number, so we have the negative sign. So this whole thing is positive. So now we can write then the right hand side is positive, and then this would be greater than or equal to R. And then here I have R and R. And I have I plus K S I minus A transpose inverse B transpose here, and K transpose, and then here we have I. And B. Then we'll just make here let R. I'm going to make it a rho times I, where rho is a positive number. And now we have I, B transpose, SI minus A, inverse A transpose. And then this would be rho and I. And then we have the same bracket again here, I. And this would be greater than or equal to rho and I. So the rho will cancel. And then now I have this term is here. And this term is the transfer function G, the open loop transfer function, the system. And K is the H. Because again, our block diagram was like this. And the vibration, this is my X times H is equal to my U. Make it capital U because it's in Laplace. The R is equal to 0. And what comes here is also U. So now if you look at the forward loop, we have X over U is equal to this. So the G will equal to SI minus A inverse MB. The H is the controller, X and U is the controller, so this is my control K. Now if you look at what we have here, so this will be I plus G and H. And then I will cancel out. And then this will be the transpose of what we have. I transpose. Now let's look at this condition now. Oh boy. We'll take 1 minute, huh? 2 minutes. And now we have I plus G H squared is greater than or equal to I. I can rewrite this equation as G H minus I and I'll take for the single input single output case the identity matrix becomes 1. So the GH minus 1 will be greater than or equal to 1. And the square will cancel out. So now what this is saying is the following. This is minus 1. And this is my GH. So this is vector minus 1. So now the difference between these two vectors is right here. So this vector is GH minus 1. And this vector has to be greater than or equal to 1. Has to be greater than or equal to 1. So now if I come here and draw circle is equal to 1. So this vector has to be greater than the radius of the circle. So this point, no way that will be inside this unit circle. This will be outside the unit circle. So this means now for the LQR, everything has to be outside here. So now if you just look at one case, for example, if I am at this point, this point is 0, amplitude is 0. And I'm going to go to -1. So the gain margin is infinity. The gain margin is infinity. This point has to be on the curve. Has to be on the curve. Why? Because this is the equilibrium point. G and H is equal to 0. So this point has to be on any characteristic curve of any system. So now if I am at this point, I have to amplify it by multiplying this 0 by infinity to bring it to -1. So I have infinite gain margin. If I am outside the unit circle, let's say, for example, I am here. I am at this location. This location is 90 degrees away from -180. So my phase margin is 90 degrees. So it's very high. Next time I will just show why the phase margin has to be greater than or equal to 60 degrees, but the gain margin is always infinity. The bottom line of this is the LQR is super stable, both from gain and from phase margin. So it has to be outside this circle. Sorry, I had to rush very fast, but everything in the note very clear, okay? And please read this section, and you are not responsible for the Hamiltonian matrix solution, okay? But I put it in so it will be complete for your documentation. Fine, I will see you on Thursday.